All right, let's take a look. Today we are doing exam review. We're going to get through density, um, changes in matter, atoms, and naming. And that'll basically put us up for tomorrow, getting through reactions and moles. Friday, stoichiometry. And then before the exam on Tuesday, we will go through thermochemistry one more time. So keep in mind, I want everything that you can turn in that I'm going to grade so that you are at a comfortable position going into the finals. Want all that stuff done by tomorrow at the latest. Otherwise, if you are failing at that point, you know that it goes to your grade on your final exam. Basically that final, if you get an A on that final, that does not merit you an A in the classroom. The final exam is what we call the minimum competency test. That means that you should be able to do that stuff if you have minimum competency of the material. Minimum meaning lowest, competency meaning understand or ability. That's what that test is. So keep that in mind. Let's take a look then at the final exam review pack. Yesterday we went down through converting. Today we want to take density into play. So let's take a look here. So a gram is used to measure mass. They do this all the time. They put like the little potato chip baggies or whatever. They don't mass that by number of potato chips. They sit there and say, okay, we're going to give you this many grams of potato chips. That's how they measure stuff. Or if you do, let's not do grams, but 1 pound is 454 grams. So if you have 454 grams of hamburger meat, that is a pound of hamburger meat. They measure that stuff by the pounds. They don't measure like, the unit of like, this is 1/8 of a cow or something like that in this this package of hamburger meat. They don't do that. So that's a unit of mass. We measure that with a scale. Liter is a unit of volume. We can measure that two ways: length times width times height, or we can measure that using some type of graduated device, like a graduated cylinder. Meter is a unit between 2 points, that is a length. So we would use a meter stick or a ruler for that. Mass, we are high tech. For those of you that came in, you saw our amazing scales. Basically, you put something on there and it tells you that mass. These can be all direct measurements. Length times width times height, for example, a centimeter by a centimeter by a centimeter. That would be known as a centimeter cubed. You could length times width times height it, or you could measure it directly with a graduated cylinder. We don't have a densometer or something like that. So in order to find the amount of particles per unit space for something, we need a little thing called a formula, mass over volume. So you need to calculate the mass or get the mass. You need to calculate or get the volume. That allows you to get density. The units for density would be grams over centimeters cubed or grams over milliliters. But the formula is density equals mass divided by volume. So if we wanted the density of a solid object that we cannot measure the length, width, and height of and get that through some type of formula, we can drop that into water. If we have a water level of that, normal, and then we drop an object in there and we get a water level of that, the distance between that and that is the volume of that object. So if it's 38.5 after we drop the object in, and it was 31 before, 38.5 minus 31.
It's 7.5.
7.5 to correct significant digits. This goes out to the 10th place. This goes out to the 10th place. So we got to the 10th place. Since it's subtraction, the units milliliter and milliliter become milliliter. Here we have an object. We know the mass. We know the volume. So we take 995.6 divided by 89.0. We get this number from our calculator. But since we only have 3 significant digits in our volume, we round it to this. Physical versus chemical changes. If something changes something to a new substance, it's called a chemical change. If you change something, but it's the same formula as before, or the same chemical compound as before, that's a physical change. If we have a puddle on the road and it evaporates, that's H2O, it evaporates into H2O vapor. That's now in the air, and on a cool night, that could recondense on the leaves or the grass blades or something like that. So that is a physical change. If we take a piece of paper and we burn it, we're not going to be able to get that back to a piece of paper. So that is a chemical change. If we crush, let's say, an aluminum can, we don't change the substance from aluminum to something else. It's just crushed. It's still an aluminum can, but it's crushed. If we melt an ice cube, let's say like you're driving home and your car breaks down and you've got ice cream and it's melted, but it's still in the container. You could put that back in the freezer and it would refreeze that. It wouldn't change the quality of it too much. That is physical. If we react, let's say we leave a piece of bologna out on the ground and it spoils, or the hamburger meat from $2 Tuesday was left out too long and it spoiled. That would be a chemical reaction. If, let's say we're having a party, football games, they're, probably shouldn't be having parties too much right now, but maybe you set out some M&M with some Reese Pieces to get that chocolate peanut butter mixture. If somebody was like, I don't like the chocolate, I only like the peanut butter, they could pick out all the Reese's because they don't have an M on them. So mixing, we could physically separate those. All right, the periodic table. So if we look, we marked on our periodic table all of the diatomic elements. Hydrogen, nitrogen and oxygen, fluorine, chlorine, bromine, and iodine. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. When it's in a gas form, and when bromine is in a gas form. Which group number are on the periodic table are these guys? Well, that's a little bit tricky. We a lot of times will do group numbers as the group A numbers or the group B numbers. But this is also the 18th group. And this is also the first group. So 1, 2, 3, 4, 5, 6, 7. This is 3. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So you could use either one of those. The noble gases are either group 18 or they're group 8A. Either one. Alkali metals, they are group 1 or 1A. Halogens. The halogens are this group right here, fluorine, chlorine, bromine, iodine. They are group 7A or 1 from 18, which is 17. The earth metals. The earth metals are the ones right next to the alkali metals. They are group 2 or group 2A. Which states of matter, solid, liquid, or gas, can be described as having the lowest density? Well, the most spread out particles, well, if solid is the most compact, and it's not always, liquid could be more compact in the form of ice versus water. Water particles are closer together than ice particles. Most of the time, solid's the most compact. Liquid the next, and gas would have the lowest density because their particles are very spread out. That means that we could take all those gas particles and push them together because they're compressible and expandable. Rigid, there's only one of these that maintains its shape over time, and that is a solid. Takes the shape of a container. That's a trick question because there's two of them that take the shape of their container. We can pour a glass of milk. And we also know that, you know, if we breathe out, it's going to take the shape of whatever container it is. Following metals or non-metals. A lot of these are metals. Metals can be hit with a hammer, shaped with a hammer. That's malleable. Conductor of heat and electricity. That's a metal. A metal spoon in a soup thing, and then you come back to touch it, it's going to be hot. What's that spoon look like? It's shiny. Which ones form positive ions? Well, remember the metals are these guys over here. Look, +1, +2, +1, +2, +3. Those are metals. Cations are called positive ions. Which ones are ductile? Which ones can be made into wire? Well, we can have copper wire, silver wire, aluminum foil. That's a ductility property. All of those, again, are metals. Which one forms covalent bonds or things that require not Roman numerals, prefixes? Nitrogen dioxide, nitrogen monoxide, right? Those are non-metals. Again, this is identifying the groups at the periodic table. Out of these, which one is a metalloid? Well, it has to be touching this line: boron, aluminum, silicon, germanium, antimony, tellurium, or astatine. Well, out of those, silicon was the only one that touched the line. Which one is a non-metal? It has to be up in this corner somewhere. Selenium. Selenium is a non-metal. Which one is a noble gas? It has to be in this group right here. Helium, neon, argon, krypton. Helium, neon right there. That is a noble gas. Which one is an alkali metal? It has to be here. Lithium, sodium, potassium, rubidium, cesium, francium. Rubidium is an alkali metal. So that is D. Which one is a transition metal? That means it has to be in here. Well, there's only one left, cobalt. Cobalt is right here in that middle part of that transition metal. That is E. Atomic theory. The atomic number represents the number of protons. The atomic number is on the periodic table. It's the single whole number digit that's right next to the symbol for every element. The mass number is not on the periodic table. It's the number of protons plus the number of neutrons. These are averages of all the isotopes. Isotopes have the same number of protons but different number of neutrons. What particles are found in the nucleus? Well, it just happens to be protons and neutrons. The nucleus is overall charged positively because of the protons. The neutrons are there to prevent the protons from pushing against each other and causing the nucleus to fall apart. Electrons surround the nucleus. They're negatively charged and they are attracted to the positive charge of the nucleus. An atom of chlorine 35. This 35 is known as the mass number. Mass number. This, also called Z, is the atomic number. The atomic number, as we said, is equal to the number of protons. So that 17 is the number of protons. 35 is the mass number. That's protons plus neutrons. 35 minus 17.
answer is 18.
That's 18 neutrons. All sodium atoms have 11 protons. Well, we said the number of protons is equal to the number, atomic number, which can be found on the periodic table. Here is sodium. It says 11. That's the identifier for that. The identifier is the number of protons. That is true. Carbon 14. 14 over 6, and the carbon is here. Carbon 14 is an isotope of carbon with how many neutrons? Well, we just did this. It's going to be that 14 minus 6. So that is 8. A sodium atom has the same number of protons as a sodium ion. Yes. Ion means they have gained or lost electrons. A sodium atom has the same number of electrons. Well, it's either gained or lost electrons. Since sodium is a metal, it has lost electrons, so that would not be true. If it loses electrons, we call it a cation. Think of the T there as a plus sign. The cation has a fewer number of electrons than it does protons. That's why it's positively charged. There's more pluses. Atoms become positive by losing electrons. We'll find out second semester why they lose electrons, but for now, cations lose electrons. Then we've got this. This is a nice big graph. They give us a bit of information. Here, cobalt 60 has no charge. But we said that that 60 up top is the mass number. It's cobalt, so we know we can look at the periodic table and find the atomic number, which is 27. We said that the atomic number is equal to the number of proteins, which is 27. Since it has no charge, that means its protons and its electrons must equal the same number, which is 27. That 27 is the Z, or the atomic number, so it goes down here. To find the number of neutrons, we need to take the mass number and subtract Z. 60 minus 27.
It's 33.
So that is 33. Same thing here, but they've given us a different bit of information. They said 56 protons. Now that tells us that the atomic number is 56. It says it has a +2 charge. That means that the number of protons must be 2 more than the number of electrons. So 56 minus 2 is 54. The mass number is 137. 137 minus 56.
It's 81.
That tells us the number of neutrons. The mass number goes on top of the atomic symbol, and the atomic number goes below it. Since we know this element has 56 protons, that tells us that it is none other than barium. So the symbol there is Ba. Yeah. Here we know it has 8 protons, so the atomic number is 8. It has 8 protons and 8 neutrons. We add those to get the mass number. It has 10 electrons and 8 protons, so that tells us that the charge is 2 more negatives than positives, so it's -2. So again, mass number goes on the top, atomic number on the bottom. Who has 8 protons? None other than oxygen. Last step for the day, nomenclature or naming. We need our periodic table for this so we can determine charges. We find sodium. The charge of sodium is +1. We find nitrogen. The charge of nitrogen is -3. So we write the formula as Na and N. We need to determine the subscripts based off of these 2 charges. The least common multiple of 1 and 3 is 3. 3 divided by 1 tells us we need 3 sodiums, and 3 divided by 3 tells us we need 1 nitrogen. We don't write the 1 for the nitrogen. Sometimes we have these things called polyatomic ions. Sulfate can be found on the back of the periodic table, and it has a -2 charge. They tell us that. Magnesium is a metal. It's found on the front of the periodic table, and it has a +2 charge. A +2 and a -2 cancel out because 2 divided by 2 is 1, and 2 divided by 2 is 1. So we're going to have 1 magnesium and 1 sulfate. Don't get confused and think we have 4 sulfates. That 4 is part of the sulfate. Here we have ammonium. As much as you want to look on the periodic table, you're only going to find that on the back. It's NH4, and it has a +1 charge. Sulfide, if it ends in IDE, it's most likely going to be found on the front. Sulfur, when it loses electrons, becomes sulfide. It has a -2 charge. So the least common multiple between 2 and 1 is 2. 2 divided by 1 means we need 2 of these ammoniums. But if I just put a 2 there, that looks like there's 42 H's. So scientists deem that we need to put this in brackets or parentheses, and they chose parentheses. Yeah. Barium phosphate. Barium has a charge of +2 when we find it on the periodic table. Phosphate, well, they gave it to us, so there's no need for us to look, has a charge of -3. Don't write that on there, though. Least common multiple math. 3 and 2 is 6, so 6 divided by 2 is 3 bariums, and 6 divided by 3 is 2 phosphates. New thing, dinitrogen pentoxide. There's no Roman numeral, and nitrogen is not a metal. There can be many combinations of nonmetals. There could be nitrogen dioxide, dinitrogen pentoxide, dinitrogen tetroxide. So they need to tell you how many nitrogens there are with this little prefix out here. Di means 2, pent means 5. Dinitrogen pentoxide. Iron 3 bromide. That Roman numeral tells us the charge of the iron. We look at iron, it does not have a charge up here. So the charge of this iron is +3. Bromide has a -1 charge. Least common multiple of 3 and 1 is 3. That means that we have 1 iron and 3 bromides. Now, I told you to memorize 3 acids. I told you to memorize hydrochloric acid. Hydro means that there's no oxygen there, so chloride is our anion. Since it has a -1 charge, it only gets 1 hydrogen. Sulfuric acid, sulfuric means it's sulfate. Sulfate has a -2, so that means that we need 2 +1 hydrogens to do that. The other one that I told you to memorize was nitric acid. Nitrate, because it's nitric, NO3, we only have 1 hydrogen. Now we have to go from the chemical formula to the name. So some of these are easy. If it's in group 1A, 2A, like calcium, we simply name it calcium. OH is on the back of the periodic table, and it's called hydroxide, so we simply call that hydroxide. NiS, nickel, is not in group 1A, 2A, silver, zinc, or aluminum. So nickel gets what we call a Roman numeral. That Roman numeral determines or tells us the charge of the nickel. Sulfur becomes sulfide, and it has a -2 charge. Since we only have 1 sulfide, that's a total of -2. We only have 1 nickel that has to cancel that out. That means that 1 nickel must have a +2 charge. We denote that by drawing the Roman numeral. NH4, that's more than 1 atom. So we look at the back of the periodic table. That's ammonium. Cl is chlorine, but since it's being written second, we change the ending to IDE. It becomes chloride. Sn is 10. It does not have a charge up here. So that means it needs a Roman numeral. Not 10. The charge of oxygen, or oxide, is -2. Since we have 2 of them, 2 times 2 is 4. So that's a total of a -4 charge. The 10 over here must then have a total of +4 because there's only one of them. That is 10 for oxide. Last one, P. P is not in group 1A, 2A, silver, zinc, or aluminum. P is actually a non-metal, so it has a negative charge. So we don't use these charge balances. We've got to use what we call the prefixes. The prefix for 1 is mono. The prefix for 2 is di. The prefix for 3 is tri. The prefix for 4 is tetra. So we have tetra. We keep the regular name phosphorus for the first element. 5 is pent, 6 is hex, 7 is hept, 8 is oct, 9 is non, and 10 is dec. So this becomes dec oxide. We again change the ending of the oxygen to IDE. Questions about any of those problems worked today? No? All right. I will then stop the recording. Doesn't mean you can cuss, Jeremy.